Hello, Mr. Ray, Mr. Ryan, right? We given this two-dimensional matrix. Okay, so you can pick the numbers. For simplicity, let's assume all the numbers are positive.
What if it isn't?
It will become more complicated if we allow the negative numbers. Okay, just for simplicity, we allow the numbers only to be positive. And the task is very simple. Just pick the numbers. Once you pick one number,
You can't do
You can't-
another number which is the same number.
now a good guess. For example, if you pick this number,
You can't pick it again.
obviously, yeah, you can't pick the numbers next to it. Okay, so it will be
You
disappearing.
mean around it?
Sorry.
You mean around it?
Yeah, and also,
Because that's not next to it.
okay, let me rephrase. When you pick the numbers in the first row, you can't pick any number in the second row or in any number above it. For example, like here, you can't put any number above it. So this row, if we pick this number, this row, the numbers, you can't pick it. And also the numbers next to it. So these two numbers, 1 and 6, you can't pick it, but you can pick 5.
I don't get how you just do the lines. You cross them out so you can't use them.
That's right.
You can't. That means you can't use 176599301.
Okay, so let me repeat. When we pick a number, we can't pick the numbers that in the adjacent lines. So if we pick any numbers in this row, we can pick all the numbers in the next line and all the numbers in the above lines. Okay. And also one addition requirement is that we can't pick the numbers on the same row next to it. Right? So two requirements. First of all, if we pick a number at the row column, yeah, we'll pick this number. If we pick this, we can't pick any of the numbers at row -1 and row +1. And also we can't pick the two numbers at row, the same row, yeah, column -1 and row column +1. We want to maximize the sum. This is the requirement. When we pick a number, we can't pick any numbers that in the above row and in the next row. We can't pick any the two numbers basically and next to it. So the one on the right and the one immediately on the left. So for example, if you pick one, then I can't pick anything here. What's the maximum you can get here?
22.
Why? Which one is 22?
7582.
Wow, okay. Any more bigger than that? Okay, 7512. Okay, so look, you pick this one, you can pick this one, but not any. Yeah. Yeah.
Does it have to be 3 times 4?
No? Oh, yeah, good question. The metric could be any size. So the thing here is that when we pick this number, all the numbers next to it, right? So these two numbers just disappear, right? We can think of it disappearing. When we pick this number, all the numbers in the next row disappearing. If we pick this number, all the numbers above it disappearing, and all the numbers below it disappearing. Okay? Yeah? This is two-dimensional. Okay.
So picking it in the middle is useless.
We pick the middle, sorry?
So picking So if you have a 3 times 3, well, now you pick a number in the middle, it's useless.
It's useless. Okay.
If you
not necessary. For example, if I'm here, like I put a million here, obviously you want this. Yeah, you want to pick the million and not the numbers. I don't care because all this is the biggest, right?
Yeah.
Okay.
Yeah, but what if it's like this? 0, 0, 0, 0.
Okay. All zeros. So yeah.
You can't really do anything.
Yeah. That's right. It's 0. Okay. So we talk about a one-dimensional problem, haven't we?
Mm-hmm.
Do you remember a street? There's a street. Each house has some money in it. Some money. Yeah.
And
2,
you want to
3.
rob. And you want to rob.
Yeah. A thief want to steal from the houses.
And you can't.
The thief can't steal 2 adjacent houses. Otherwise, the police will be called. The alarm will fire off. Right? Remember, this is one dimensional, right? So at that problem, we want to find out the maximum sum of non-adjacent numbers, right? Yeah. So for example, 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. So we want to pick the sums pick the numbers that sum up to the maximum, but we don't want to pick the numbers that next to each other. If we pick 2, we can pick 1 and 3, but we can pick 4 or pick 5. At the time we talk
I'll
about
pick 5.
Sorry?
I'll pick 5.
Yeah, but you can pick more, so pick 5,
3.
3,
1.
1. Yeah, that's maximum, right? Am I right?
9.
Yeah,
That's 11.
Yeah, that's 11. That's the maximum you can get.
Yay.
Okay, so we talk about that. Remember, we talk about the dynamic programming. Yeah, we use this one-dimensional. How is that useful? Come on, how is that useful? If this is one-dimensional, if I'm saying this is one row, okay, one row. If I'm saying this F row returns the largest non-adjacent sum, right? If I'm saying that F row returns the largest non-adjacent sum for the row, for this row. So how is that useful? This is 2D, this is 1D. If we're looking at this, what's the largest non-adjacent sum? Just for this one. If we can't pick 2 numbers next to each other, what's the largest sum you can pick here?
7 and 5.
7 and 5, okay, 12. What's the largest sum here?
12.
12, nice, yeah? 12. These 2, yeah? These 2, yeah? What's the largest sum here? 10, yeah? 10, A and 2, okay? Okay, now, looking at this one dimension, row by row, we know this, yeah? Okay. So, what about these 3 numbers? 12, 12, 10. It's the same, we can apply the same algorithm again, right? 12, 12, 10, what's the largest sum you can get? It's like,
22.
yeah, 22. So the sum is 22. If we pick this number, all the numbers next to it disappearing. The number on the left disappearing, the number on the right disappearing. Because on each row, we can't pick 2 numbers in a row, right? So we can apply this algorithm, the police and robber problem, one-dimensional. So look at this, we can get 12 if by looking at this row only. If we can get 12 on the second row, we can get 10 on the third row. When we pick this number, all the numbers next to it, the above and below on the adjacent rows will disappear, right? So it means that if we pick the number 12 here, we can pick any of the numbers on the next row, right?
Yep.
So it means that we can apply this, alright? 2, 3, 5, 7, 6, 1, 2, 3, 2, 1, 2, 4, 3, 6, 7, 2. Okay? What's the largest non-adjacent sum if you can find, pick in this matrix? What's the sum?
Let's see. Let's see.
Okay, so what's the first one you can get? What's the sum of the largest non-adjacent?
Oh, I can't see.
Now just look at the first row. What's the...
10.
Yes, it's 10, yeah? So it's 10. It's 10, okay? What's the second one? 9, right? I can pick this and this, 9, right? What's the third one?
6.
6. What's the last one?
Is it 10?
10, okay? Now, given this, what's the maximum you can pick?
20.
20. So it means that we can get 20 by picking this one, this one, this one, this one. Yeah? Is this satisfying the requirement? If we pick this number, we can pick any of these and not this one. We can pick this one, not this one. If we pick this number, we don't pick any of those. Yeah, we can't pick any of those. Yeah. So it satisfies the requirement. Yeah, got it?
Yeah.
Largest sum of how do you spell adjacent? J-A-C-E-N-T, yeah? Numbers. We talk about different solutions. The core idea is the dynamic programming. Fi means that the largest sum that if we're looking at from the beginning to the ith number, so Fi equals maximum. For this number, yeah, look, there are a few numbers. This is ith number, yeah. If we're looking at this, Fi, what does it equal? It equals to Fi minus 1, right? This one. But once we have this, we can pick this, right? Or fi minus 2, if we pick here, then we can have this plus nums I, right? If we pick this number, we can pick this, but we can't pick it. So fi equals the maximum of fi minus 2 plus this number, right? Or fi minus 1. I know this is dynamic programming. Yeah. We're remembering this fi. We don't need to calculate it again and again. So I'm just going to write a iterative version of it, yeah? And you can do it in the top-down dynamic programming or bottom-up dynamic programming. Yeah. And then this is much more like a Fibonacci number. Define f numbers. N equals the length of numbers. If n equals 0, return 0. Nothing, then we return 0. If n equal 1, if there's only one number, then we return it. Return numbers 0. Okay? Then a, b equals 0, 0 for I in nums. A, b equals the b maximum a, this is the first number, plus I and b, and return b. The idea is that we're going through every time a and b. A means the numbers that the largest sum we can get by picking this number and the numbers prior to it, but not including the immediate previous one. B is the largest sum by picking the previous number, but obviously we can pick the current one. Okay? So once we have this f function for this two-dimensional, then we can just return max, return f r for r in original metric. Then we apply this again, return f.
Well, we calculate the sum of each row, and then
then what?
and
So we calculate the largest sum. You know how to solve this one-dimensional problem, right?
yeah,
We're applying this f function, right?
yeah, and then you calculate the sum of each row, and then you calculate the greatest sum of the rows.
Over what? Come on. So
Rows of sums.
why can we do this? First of all, what do we need to do with these numbers?
It works because you like if you pick a number, you can't choose the left or right to it. So and you can't choose the row below and below. So the sum works as like it's not next to each other, like adjacent or whatever.
Adjacent. Yeah.
And and then we add the sum, yeah.
So there are two requirements. So let's look at each row. So if we pick one number, we can pick two numbers next to it, right? So that's the one-dimensional problem of the please the thief problem, right? Am I right? And then if we have this the largest sum for each row particularly, we can apply this algorithm to it. Because if we pick one number from first row, we can pick any number of the second row, right? So if you look at it that way, perspective, then that's another dimension of the police. And
also the row above.
Exactly. So the takeaway today is that if we are solving this kind of problem, we can apply this 1D solution twice to solve it. Am I right? Ryan, what have you learned today?
About numbers.
What do we do with the numbers?
Try to get the biggest number.
So what are the requirements when we pick the numbers?
You can't, if you pick one number, you can't pick the number on the left or right or the row above or below.
Yeah.
Don't worry, all dry.
So we want to find out the largest sum for the non-adjacent numbers of each row, right? And those numbers, then we can apply it again. So for example, the largest sum for the first row is is what? 8, right? It's 8. So I'm gonna put an 8 here. The largest sum of the second row is
14.
14. The largest sum of the third row is 10.
10.
The largest number of 4, right? I know what to do with
Isn't
these
it
4 numbers.
3?
Yeah,
Isn't it 3?
Oh, yeah, sorry. Yeah, you're right, okay. So,
It doesn't matter anyway.
so what do we do with these numbers?
Add the two greatest numbers, which is in this case 14 and 10, and then you add them up.
14 and 10? Why 14 and 10? I pick 14, I can't pick 10.
Oh yeah.
So what are the numbers maximum?
10 and 8.
10 and 8, yeah. Okay. Because we pick any number of the second row, we can't pick any number of the third row. So if we transpose it, we just have to apply this again. This is how we're solving the one dimensional, right? Fi equals maximum of Fi minus 2 or Fi minus 1 plus Fi minus 2 plus the numbers at I. Okay. And this time complexity is On. So we applying this twice, the time complexity is still On, right? So On, and we'll get this number On. Okay, that's it for today. Bye bye.
Bye.
Bye bye.